Okay, so let's begin for today. Okay, the syllabus is already in auto class. Well, I will be updating it. It has the general information about the course, the textbook, supplementary material, what we will be covering. And well, the first 6 we will definitely cover. The remaining 3 items over there depends on whether we will have time or not. Depends on how fast we will be proceeding during the semester. You will have the midterms, final, the pop quizzes, pre-reports, and assignments. The pre-reports and pop quizzes will be basically a bonus. And assignments, well, I didn't yet decided whether I don't know if I will be able to give you regular assignments or some online assignments. If it will be online assignments, they will be bonus. Or if it's not, then, well, I didn't yet decide on the percentages, let's say. The dates we will be fixing the dates probably next week, so your other exams will also be probably determined by that time. I will try to make it in class if I can arrange some other empty classroom in the nearby at the time of our lectures. Now, what are these pre-reports? Are you familiar with pre-reports from last year? Basically, it's the same idea. I want you to come to class having already read the material. I will announce which sections you should read before coming to the lecture. I will probably announce them tonight, and then you will be handing them in by Monday before the first lecture next week. Okay. And there is also another, I have created some discussion forum here where you should have probably received one email already from the forum. Most of the time I am aware that you make some Facebook groups or WhatsApp groups where you can discuss the matters about the course. But you can also use this forum here if you like. You can also ask your questions anonymously without anybody knowing who you are. Now, the advantage of using the forum in auto class will be we will be also following your discussions. So if you are taking a wrong direction, we will be able to guide you to the correct answer. We will not be giving out just simple answers. It won't be just you asking questions, me and your assistants answering your questions. I would rather first you discuss it among yourselves. We will be following the discussions and make the corrections if necessary. If there are no answers coming, then we will answer. So if you have any questions about the course material, if you couldn't ask in the class during the discussions or after the class, you can also use this auto class forum. Now, so today, let's start the material of today. So do you have any questions before we continue? Yes, I will not be taking any additional attendance. I will do pop quizzes. No. Well, I used to do it in first-year students. So if you don't attend the pop quizzes, I wouldn't allow the first-year students to take the final. But, well, at least I'm kind of against taking attendance, to be honest. But my personal experience is that at least first-year students, if you don't take attendance, they don't show up until the end of the semester when they start complaining that they have to pass the course. So that's why I started somewhat taking the attendance. Well, we are second-year students. This is the first time I'm teaching the second-year students. So at least in my first experience, I would like to leave the attendance outside. So the pop quizzes will be bonus. It will be probably 5% bonus. So if you attend all the pop quizzes, you will get an additional 5%. If not, nothing. So hopefully you will be attending the lecture throughout the semester. And okay, so last Thursday, the last thing we did was we had discussed the Lorentz transformations. Which allowed us how to translate certain measurements made by different observers. We had the reference frame O and the reference frame O prime, x prime, y prime. So an event happens This event is observed to happen at the point x prime at the time t prime by the observer at O prime, moving with that O prime reference frame. And the same event is observed to happen at the point x at the time t by the observer fixed at the point O. And the O prime reference frame was moving with a speed, let me use the capital V, with a speed capital V. Then we said that, okay, so if the xt and x prime t prime are related with each other through the relationships, x is equal to x prime plus vt times gamma, and t is equal to, again, gamma t prime plus v over c squared x prime. Or you can just invert these relationships and you would get x prime is equal to gamma x minus vt, and t prime is equal to gamma t minus v over c squared x. If you note the difference between these two sets of equations, the only difference is the change of the sign v here. Oh, sorry, this is here there's a minus sign. The only difference is the change of sign v. That also makes sense because just like you can use that transformations to translate the coordinates of O prime to O coordinates in this form, where that v is nothing but the speed of the other reference frame, let's say. In that case, it's the observer O, and the other reference frame is the O prime reference frame, and its speed is v. But you can also do the same thing from the perspective of the O prime observer. For the O prime observer, the reference frame O is the other reference frame is moving with a speed minus v. So that v is actually, in both of these relationships, that v is nothing but the speed of the other reference frame, or the velocity of the other reference frame. And then using these relationships, for one thing we derived the addition of velocities. So we said that, just to repeat one of the examples, the velocity of an object measured by the observer in O prime reference frame would be equal to delta x by delta t. Both of these quantities should be measured in the reference frame O. But we know how these are related to the measurements in the reference frame O prime through our Lorentz transformation. So this was gamma delta x prime plus v delta t prime divided by gamma delta t prime plus v over c squared delta x prime. We just canceled the gammas. We divided both sides by the numerator and denominator by delta t prime. And we obtained this was v prime vx prime plus capital V divided by 1 plus capital V times vx prime over c squared. So this was one of the one of the addition of velocities. Here vx prime is the speed measured by, is the velocity, the x component of the velocity measured in the other reference frame. V is the velocity of that other reference frame. And you just sum them up. This was what we had in Galilean relativity in 109. But we have this additional correction due to relativistic effects. And if you just look, if you just assume that c is infinitely large, or all the velocities are very small relative to this c, you can just ignore this term and you recover the Galilean relativistic result. The addition of velocities that you have seen in 109. And this gamma factor, we will often be using it. That is just 1 over square root of 1 minus v squared over c squared. Again, this v, by the way, here is the velocity of the other reference frame. Now, any questions up to here? Hı hı.
Yani ikimiz de ekleyeceğimiz zaman onların hangisini neye yani orada biraz şey düşünüyorum.
What do you mean?
Yani şey olarak reference frame'lerde kafamda hangisi Vx prime hangisi V şey yapamıyorum.
Well, the thing that you should keep in mind is that, let's say, this is the speed, the x component of the speed measured in one reference frame. Okay, this without the primes. With the primes, it's the x component of the velocity measured by the other reference frame, whatever the other reference frame is. This v is the velocity of the other reference frame relative to the original reference frame, let's say. And then you just have 1 plus this factor over there. So all the quantities over here are, in a sense, related to the other reference frame. And this is your original reference frame. Which one is the original? Well, up to you. Just choose one as your original reference frame and the other one as the other reference frame, and these relationships should hold, as long as you are consistent.
Hocam original reference frame dediğinizde hareket etseydik bir yana doğru, o zaman nasıl olurdu?
You see, when I'm saying the original, you see, when you are talking about speeds or velocities, you are talking about speeds relative to some original reference frame, relative to some reference frame. You are not really talking about the object itself. You are not talking about a quantity which is intrinsic to the object, let's say. You are always referring implicitly to a reference frame. So when I say measured by this reference frame, measured by the O reference frame, I cannot really talk about the speed of the O reference frame. Of course, it is moving relative to the other one, but so what?
Last lecture we did the travel of the mirror into the Earth's atmosphere. We didn't use the Lorentz transformation. Why did we use the formula of the T and the gamma factor?
To derive the length contraction. Let's derive the length contraction from using Lorentz transformations. Well, let's see. We are talking about the length measured in two different reference frames. Right? So we are looking at, what do you mean by length, by the way? What's the length of an object? Measured by? No, that's the 1 meter. But, I mean, when you are measuring an object, measuring the length of an object, what do you do? You take a ruler, right? You take a ruler. Okay, I don't have a ruler, but let's say this is my ruler. I just compare this ruler with my table. Or another thing I can say is, if I know the coordinates of the points, I can say that the length of an object is the difference between the distance between the end point and the initial point. Now, for simplicity, let's just assume that everything is one-dimensional, so we are only interested in the x-axis. So the other reference frame is moving along the x-axis, and my object is also along the x-axis. Now, of course, when the objects are moving, we have to pay attention to one thing. So I need to know the differences in the x-coordinates to determine the length. That's what I'm looking for. I have to determine the length of the beginning and end of the object at the same time. Okay, this will be the crucial difference. I have to determine the beginning and the end of the object, the coordinates of the object, the coordinates of the beginning and the end at a given time. If the object is moving, let's say, if I'm moving, and if I measure the beginning of an object at one time and the end of an object at the other time, then I'm not really determining the length of the object. So that is one thing we have to pay attention to. Now,
So our points must be considered as events?
well, the events here are the measuring of the coordinates. You measure the coordinates of the starting of the object, and you measure the coordinates of the end of the object. And these two events, at least if you are measuring length in your reference frame, these two events should happen at the same time in your reference frame. Now, let's see. let's say that somebody has measured the length of an object at a given different reference frame. So that is basically the endpoints differ by delta x prime. The endpoints differ by delta x prime when delta t prime is equal to 0. This is the length measurement in the L reference frame. So delta x, the Lorentz transformation is right at the top. So delta x is equal to gamma delta x prime plus v delta t prime. So it's gamma times delta x prime. But there's one problem. You see, we had defined the gamma factor to be like this. Gamma factor is larger than 1. So it seems as if we don't have length contraction, but it seems we have the length expansion. So what's wrong? The sign of the velocity. Well, delta t prime is 0, so even if I change the sign here, it doesn't make any difference. Why should it be 1? V is not 0.
Oh, it's not 0.
No, because you see, we have the other reference frame that is moving. And the observer fixed in that reference frame had measured the length to be delta x prime, let's say L. So what's wrong in this derivation? That's what I'm asking. We already know that that should be wrong. If the length of an object is measured as L in the other reference frame, in my reference frame, it should be L over gamma, not L times gamma.
Isn't the x prime is the particle's distance? I mean, what the distance particles?
No, you see, when I say delta x or delta x prime, that is the separation in the x coordinate of two events. In this particular case, one event happens at the beginning of the ruler, beginning of the object. The other event happens at the end of the object. What's wrong over here? What is delta t? Let's look at delta t. We looked at delta x. It seemed wrong. Well, let's see. We know that delta t prime is 0. I didn't say delta t is 0. Let's see what is delta t. Well, the transformation is over there. So it's just gamma delta t prime plus v over c squared delta x prime. Well, delta t prime is 0, but this is not 0. So delta x prime is the length of the object in the other reference frame. You see, because the beginning and the end of the objects are measured at the same time. That is how we define the length of objects. You have to determine the positions of the beginning and the end of the object at a given time, not at different times. So delta x prime is the length of the object in the other reference frame, but delta x is not the length of the object in the original reference frame because the two measurements of the positions of the beginning and the end didn't happen simultaneously. We just measured the beginning and the end of the object at different times. But the object has moved during that time. So the difference in the distance between the beginning and the end of the object at different times doesn't give me the length of the object. So I will make let's say I will be making a shortcut, or I will be cheating. So basically here it also stresses the fact that although we derive the length contraction expression we have relates the length of the object in its rest frame, in the reference frame that it is at rest, to the length of the object observed in another reference frame in which the object need not be at rest. So the length contraction expression is valid only in that case. If, for example, there is an object flying by, I measure the length of that object to be a given length, and according to him, the object is also moving, and he takes my measurement and multiplies it by the length contraction factor. The length he will obtain will not be the length he will be measuring. He is doing something wrong, because the length contraction formula only relates so-called the rest length of an object to its length when it is moving. Okay, now let's make this assumption. So in the other reference frame, the object is at rest. Now, why does this simplify it? Because now I don't need to measure the beginning and the end of the object at the same time. The object is at rest, so they are not changing. So I can measure the beginning of the object and the end of the object at any time I like. I don't need to have this delta t prime is equal to 0 constraint now. But I still have, if I am measuring the length, my measurements should happen simultaneously. Delta t should be 0. The delta t of the measurements that I make should be 0. Well, what does it tell me? If delta t is 0, well, this just implies that delta t, which is gamma delta t prime plus v over c squared delta x prime should be 0, or delta t prime should be equal to minus v over c squared times delta x prime. You see, delta x prime is the length of the object in the other reference frame. So in the other reference frame, the measurements I make, remember I'm making two measurements. I'm measuring the beginning of the object and the end of the object at the same time in my reference frame. But as we had discussed also in the previous lectures, this simultaneity is a frame-dependent concept. If I measure the beginning and the end at the same time, that's simultaneously in my reference frame, they will not be simultaneous in the other reference frame. And the time separation between these two measurements in the other reference frame should be given by this expression. So I should measure the beginning, the one end of the object before I'm measuring the other end of the object in the other reference frame. But it doesn't make any difference, because in the other reference frame, my object is at rest. It's not moving. The beginning and the end points didn't change during my measurement. Now let's take this and let's try to calculate delta x. Well, delta x was gamma delta x prime plus v delta t prime. Now I know what delta t prime is in the other reference frame. This is equal to gamma delta x prime plus v times minus v over c squared delta x prime, or gamma 1 minus v squared over c squared times delta x prime. And remember, gamma is nothing but 1 over the square root of that factor. So that tells me that delta x is equal to square root of 1 minus v squared over c squared times delta x prime. Now we have the correct length contraction formula.
What do you mean by correct?
Well, we had derived this also using the example of the muon, for the muon, for example.
So it's the same thing.
It's the same thing, but derived using Lorentz transformations. So there is this so-called paradox. You might have heard of it. Just imagine there is a car and it has a garage. And let's just assume that the car fits into the garage just barely. So you have the garage. And inside there is a car. It just barely fits in. Now let's assume that the car tries to enter the garage very fast with speeds close to the speed of light. In the reference frame of the car, the garage will length contract, so the car will not fit. In the reference frame of the garage, in the reference frame in which the garage is at rest, the car will length contract, and hence it will easily fit. Which one is correct? So your answer is? Okay, first give me the answer. Okay, the car fits easily. Car does not fit. Both observers are correct. You see, this is, let's say, observer 1. This is observer 2. None of the observers are correct. So observer 1 is the observer fixed in the reference frame in which the garage is at rest. Observer 2 is the observer fixed in a reference frame in which the car is at rest. So how many of you say that it is 1? How many of you say that it is 2? How many of you think that it is 3? How many of you think that it's 4? Well, both of them are correct. You see, the idea is if you ask the second observer, which is the one in the garage, no, it's the one fixed on the car, moving with the car, this basically the driver. He will say that, okay, at a given time, when the front of the car reached the end of the garage, the back of the car was still out, and hence he will claim that the car did not fit. Whereas the observer 1 will say that, no, you are wrong. You are wrong because when you are saying at equal time the events that you are calling at equal time are not simultaneous. You measured one before the other one. If you say that if you do it properly, when you measure the start and the end of the car at the same time, it easily fits. Basically, why do they disagree? Because they disagree on what is meant by simultaneous events. So because of that, both of them are correct.
Hocam peki causal bir event olsaydı ne olacaktı?
The order of causal events do not change.
Yok şey kastediyorum mesela. Garajın kapılarında bir tane atıyorum bir sensör var. İkisinde aynı anda arabanın...
What do you mean by simultaneity? You see, when we are saying that simultaneity is relative to the observer. If you say that simultaneous, or if you say that at the same time, I will ask you relative to which observer? Besides telling me relative to which the reference frame you are using, the concept of simultaneity doesn't make any sense.
Say car.
Okay, so you are in the observer 2. Okay.
Car does not fit, so both ends are sticking out of the garage. So there are both sensors in the door of the garage.
Okay.
If it sees car, it if one and one, true and true, it lights a light bulb.
Okay, so the observer in the car will see the light bulb, right? That's what you are.
Flash, yes.
Okay.
However, for an outside observer, he will not see the lamp. However, but how can both happen?
So let me rephrase the question if I understood it correctly. He says that let us assume that there is a sensor here and there is another sensor over here. So when the front of the car passes through the end of the garage, that sensor will be lit. When the back of the car passes through this end, that end will also be lit. So we have two lamps, and he further says that let's imagine a third lamp. Where would you like to put it?
Inside of the garage.
Where? At which point?
Roof.
Yeah, let's say in the middle. Let's say assume that you put it in the middle at this point. This sensor over here looks whether these lamps are on or off. And you will say that whether this lamp looks at them whether they are on or off at the same time, right? No. Yeah, yes, that's at the same time, but that will be true for the observer which is at rest with the sensor. The observer that is moving will complain that that sensor doesn't work properly because it is lit for events that happen non-simultaneously. So they will both, if the light lamps, well, the light will turn on, barely, let's say. Both observers will see the light. But one of them will say that, oh, great, so the two ends sticked out. Because that sensor turned on when it saw these two lights at the same time. But the other observer will complain. It will say that, no, it didn't see the lights at the same time, but still it was lit. So the sensor is not working properly. That will be his complaint.
How does the car easily fit? According to the other observer, how does the car easily fit?
According to, well, so we have the observer fixed at the garage. This observer says that, great, the car is now length contracted. It is shorter than the garage, so it will easily fit. At the same time, at the time that the tip of the car reaches the back of the garage, at that time, the back of the car is already inside. At the same time. But the other observer will say that, no, those two events didn't happen at the same time. So you are not measuring the length. You are not doing a proper job. That will be the complaint of the other observer. Other questions?
Hocam, garajla hareket olsaydı, o zaman garajla hareket ediyor olsaydı, o zaman yukarıda...
Relative to which reference frame? Are you introducing a third reference frame? But why?
Öyle bir durumda o zaman yukarıda yaptığınız hatayı yine yapmış mı olacak?
Which one?
Garajda yaptığınız hatayı. Eğer garajla hareket olsaydı o zaman...
Well, you see, we didn't do any mistake over there. All our computations are correct. The problem is, what do those computations mean? All these computations, all these results, including this result over here. Where did I have it? Including this result over here. This is also correct. It's not wrong. But this delta x is not the length of the object. It's how you interpret it makes the difference. This is not the length of the object because you are not measuring the beginning and the end points of the moving object at the same time. That wasn't. The interpretation is wrong. The derivations are all correct. Well, if you introduce a third observer, it might happen that the third observer is moving with half the speed of the car will contract, the garage will contract by the same amount, so they will all be of the same length, and he will say that it barely fits. But still no problem. It's just you are comparing two different reference frames at a given time.
Üçüncü observer ikisinin de boyunun aynı anda aynı boyda olduğunu nereden biliyor?
He has to measure it. And of course, in his own reference frame, he has to measure it. Either he has to measure the speeds and use the length contraction expression, or actually go and measure their length.
Hocam ben şöyle anladım. Araba geçerken yine sensörler doğru çalışacak. Arabanın önüne geldiğinde çalışacak ama aynı anda olmayacak ışıklar.
Yes, depending on which observer you look at, they might not be at the same time. The concept of simultaneity changes from reference frame to reference frame. Other questions? Well, let's look at time dilation. Well, the time dilation is basically how the measurement of time difference between two events changes from observer to observer. So what we are interested in is, let's say there is a difference in time between two events in the other reference frame, delta t prime. How is that related to delta t in my reference frame? This is the relation we have, gamma delta t prime plus v over c squared delta x prime. Now, this is the time difference between two events. Now, what can be these two events? For example, the second arm of a clock comes to 5. This is the one event. And the second clock of the same clock comes to 6. This is the same event. This is the second event. So the time difference between these two events will be just 1 second in the reference frame in which the clock is at rest. Well, if the clock is at rest, delta x is x prime is 0. This is 0 in the reference frame in which the clock is at rest. So delta x prime is 0, which means delta t is gamma delta t prime. This is the length dilation expression we have. So if the clock shows 1 second, the clock that is moving with us, moving relative to me, let's say, if the clock shows 1 second, delta t prime is 1 second, my time has passed more than 1 second because gamma is larger than 1. So we have the time dilation expression. In this one, the crucial thing was delta x prime should be 0. The time dilation basically refers to the time passing in an observer, in a clock that is fixed in the other reference frame, and compare it with the time passing in a reference frame in which the clock is moving. If you introduce a third reference frame, for example, let's say there's a clock moving, I measure the time that has passed to be 3 seconds in the clock. And if I'm moving relative to you, let's say, and when you measure the time, it need not be 3 seconds. It need not be, I don't know, 5 seconds. It will not be, the time that you measure need not be related by this expression. The time of the clock and, right, there's the time of the clock and the time that you measured will be related by this relation. But you cannot just take the time that I measured of the clock and use this expression to obtain the time that you will measure. So when you're inserting a third reference frame, quite often you have to be a bit careful, otherwise you will make mistakes.